In this lecture, we're going to talk about some of the first connections between the derivative and the Riemann integral in our way to working towards the fundamental theorem of the calculus. And this first step is the mean value theorem for integrals. Okay. Suppose that f from the closed interval a, b into r is a continuous function. Then there is a real number c in the closed interval a, b such that f of c is equal to 1 over b minus a times the integral from a to b of f of x dx. Okay, in other words, we have a point wherein the function achieves the average of the function. Okay. Now, to prove this, we're going to just say take a partition, the trivial partition AB, and we can calculate that LP of f is equal to m times BA, and UP of f is capital M times BA, where little m is the minimum and capital M is the maximum of the function f on the closed interval AB. Therefore, we can simply, by plain principles, get that m times b minus a is less than or equal to the integral is less than or equal to capital M times b minus a, and then by dividing through everything by b minus a, we get that our average of the integrals is between little m and big M. Okay, so take that and put a pin in it. Now let's see, apply the intermediate value theorem to that. Since f is continuous, there are points x1 and x2 in the closed interval AB such that f of x1 is equal to little m and f of x2 is equal to big M. So by the intermediate value theorem, there is a number c between x1 and x2 such that f of c is equal to that intermediate value between the two. And so there we have that proved. Okay. We're going to apply this when we take a derivative of a very specially defined function. Take a function f, continuous, defined on the closed interval AB going into R, and use that function f to define a new function. Capital F of x will be equal to the integral from a to x of little f of t dt for every x element of the closed interval AB. Okay. Now, if we do this, then the derivative of the big F evaluated at c is just the same as the integrand evaluated at c. Okay. To prove this, consider f of c minus capital F of x over minus f of c over x minus c. So what we're going to do is we're going to show that this difference quotient and f of c can be made arbitrarily close as x approaches c. All right, now note here I can calculate that f of x minus f of c over x minus c is equal to 1 over x minus c times the integral from c to x of f of t dt. This is just by doing standard manipulation of integrals. We don't, there's nothing tedious required here. Now, note the following. There is a c prime between x and c such that f of c prime is equal to the average value of the function of f on the interval from c to x, okay, as we have stated here in this formula. Okay, now let epsilon greater than 0 be given, and choose delta greater than 0 so that if x minus c is in absolute value is less than delta, then f of x minus f of c in absolute value is less than epsilon. Okay. Now let's assume that the absolute value of x minus c is less than delta and see what happens. Choose our c prime between x and c so that it does what it needs to, so that it hits this intermediate value. In this case, c prime will be closer to c than the distance delta. Okay, so we can say that we can see here that f of c minus 1 over x minus c, x to the integral c to x f of t dt is equal to f prime of c minus f of c, and that is less than epsilon. Okay. And so we're done. The f prime of c is equal to little f of c.